In this video, we are going to translate sentences involving nested quantifiers. We'll start with a fairly straightforward example. The sum of two positive integers is always positive, and we're going to translate this into a logical expression. And that means we're really going to focus on quantifiers. We can also use propositions here, but I'm going to show you how you can also do it without a proposition. There's really just a lot of different ways that you can do this correctly, which is why it's a little bit confusing, because you could get a different answer than the person sitting next to you and both be correct. So let's take a look at how I could write this correctly. First of all, I'm dealing with the sum of two positive integers. So my first step when I'm thinking about translating is, instead of looking at a phrase like the sum of two positive integers, I'm going to look at something like, for all integers, for all positive integers, x and y. So that's the of two positive integers. Instead of two positive integers, I'm replacing it with x and y. Then I'm looking at the sum is always positive. So how could I write the sum is always positive? Well, x plus y is greater than 0, because always positive means greater than 0. So have I done what I needed to do? No, I'm just getting myself ready. So how could I now take my rewritten statement in English and write this as a proposition or using quantifiers? So here's one way, and again, there's more than one way. So I can say, for all x and for all y, if x is greater than 0 and y is greater than 0, again, that's giving me the positive part of this. So if that's true, then x plus y is greater than 0. So this is one way I can do this. So for all x, for all y, if x is greater than 0 and y is greater than 0, then x plus y is greater than 0. The domain here would be all integers. And that's why I had to specify here that x and y were greater than 0. Here's another correct way I could do it. I could say, for all x, for all y, x plus y is greater than 0. Now, how could I say that? Well, if the domain was positive integers. What's another way I can do this? Let p of x, y represent or denote x plus y is greater than 0. Then in either of the statements that I just wrote, I could replace x plus y is greater than 0, with p x y. So we can see there's a lot of different correct ways that we can do this. So looking at this example, we can see things are just a little bit different, and the way that they are different is that I've already given you the predicates. I've already told you EXY denotes X sent Y an email, and TXY denotes X sent Y a text. Now, before we go on to this question, I just want to point out something to you that might be a stumbling block. Here, I've written EXY, and essentially that just means whatever I put first is the person who's sending the email, and whatever I put second is the person who is receiving the email. Same here, I have TXY, X is the sender, Y is the receiver. So if later you see me write EXY A, B, that would just mean that A sent B an email. Hopefully you get that. So now let's continue on. We are going to translate these statements given the domain of students in class. So we'll start with A. It says every student in the class. Every student in the class. Hopefully your math brain says, hey, that means for all students in the class. And then sent an email to Joe. Every student in the class sent an email to Joe. So I could write for all X, X of course is a student in the class, for all X, email, for all X, E, X, Joe. Here's one way I could write this. So for all X, E denoting X sent Y an email, so all students sent Joe an email. Now it might be that you're not cool with Joe corresponding with himself. You're saying, well, Joe's not going to send an email to himself. So I could modify this to say for all X, X does not equal Joe. So if X does not equal Joe, then that student sent an email to Joe. So all that does is take Joe out of the senders. So as long as X is not Joe, as long as the sender isn't Joe, everybody else in class sent an email to Joe. Now let's take a look at the second one. There is a student in class. Again, there exists, hopefully your math brain says the backwards E, which is the existential quantifier, not to be confused with the regular E that says sent an email. So there is a student in class who has not received a text or email from any other student in the class. So there exists a student in the class, and you can do any letter that you want there. So and just be careful, if I choose X to be the student in the class who hasn't received the text or email, then that means he's going to go here where my Y is. So if that's going to trip with your brain, say there exists a student in the class such that all other students in the class, again, X does not equal Y because we're not worried about that student sending himself or herself a text or email. So if X is not the same person as Y, if X and Y are unique students, then has not received a text or email. So not, and then the student received a text or the student received an email. Now, if you have been paying attention, we know that we've got this negation here. And so another way I could write this is that for all, or there exists a Y such that for all X, if X does not equal Y, then not EXY and not TXY, which of course means that X did not send an email to Y and X did not send a text to Y. Let's look at another example, and this one actually goes in the opposite order. I've given you the propositions, but this time I've given you the statement written using propositional logic and want you to translate to English. So let's get started. We know T of X denotes X uses TikTok, and FXY denotes X and Y are friends. So we'll translate into English where the domain is students in class. So I'm going to kind of break this into parts. We've got for all X, and then we've got T of X, or, and then let's pick another color. There exists some Y, and I'm running out of colors, such that all of this is true. So let's see what we can come up with. For all x means for all elements of our domain. Domain is students in class. So for all students in class, what do I know? T of x. T of x denotes x uses TikTok. The student uses, oops, I was going to use purple. For all students in class, the student uses TikTok. And then we've got, or there exists, I'm going to say another student because it's not the same student as the original. There exists another student, and then this stuff in blue says T of y, which means y uses TikTok, who uses TikTok, oops, TikTok, and what else? fxy, whoops, wrong color. fxy. fxy says x and y are friends. So who uses TikTok and is friends with our original student? Now, is there a better way to write it? Now that I have it in English, can I simplify it maybe just a little bit more? I can say all students in class use TikTok or are friends with another student who uses TikTok. Yay! That's all there is to it. Just for fun, you can go ahead and try this one on your own before we go over the answer together. So I suggest you press pause, try both parts of the question, and then press play. Or just follow along with me. So let's take a look. We have let SXY denote student X has taken class Y for the domain of all students at BU and all classes at BU. So translate the following. So there exists an X such that SX, MA315. So what does that mean in English? Well, there exists a student X who has taken MA315, which is of course discrete mathematics at Bellevue University. The second one, this one gets a little crazy. I'm throwing X, Y, and Z. And is that fair? Well, sure it is. So this one says there exists an X and there exists a Y such that for all Z, X does not equal Y, and S of XZ, if and only if S of YZ. Well, great, but what does that actually mean? So what I know is X is a student and Y is a student, and I know that because the first term always has to be a student. And my very first sentence says that I've got a student X and a student Y. So there exist two students, and before I write two students, I want to focus in on this one right here. What does X does not equal Y mean? That means these are not the same person. So there exist two distinct students. So I've gotten through there exists, I've gotten through, hey, they're not the same person,
And now, what does all of this business mean? Well, we can assume that Z is some class, right? So any class at BU. And we're saying that student X is registered for class C, or has taken class C, and student Y has taken class Z, and this one's if and only if. So I could write it out in a longer sentence and then shorten it down, but I'm just going to go straight for the gold. So there exist two distinct students at BU who have taken the exact same classes. Because essentially what I'm saying here is X will only take it, or X has only taken it if Y has taken it, and Y has only taken it if X has taken it, which means they have to have only taken the exact same class. Okay, now we're translating a statement from English into predicate logic using quantifiers, and we are not given what those predicates are. So this is a little bit harder. And so essentially what we need to make sure that we do here is we have to tell everybody what our predicates will be. So let PXY denote what? So there's a man that has taken a flight on every airline in the world. So I'm going to let PXY denote X has taken flight Y. Now, why did I do that? Because I knew I was basically dealing with three things. So taken a flight, and that flight is on every airline. So that's the three things. So PXY says X has taken flight Y, so X is the person. And then we're going to let Q of XY, or nope, let's go YZ just to not make anybody get a headache. YZ denote that flight Y is a flight on airline Z. So whatever letter I use for a flight, I'm just going to make sure I use that letter again as a flight. So now back to my sentence. I now have all of the tools that I need to be able to write this sentence. I'm going to say, there exists a man. There is a man. There exists a man. What do I know about this man? That he has taken a flight on every airline in the world. So for all airlines A, there exists a flight such that, and then PXY, remember this is the man has taken the flight, and Q denotes that flight is on airline Z, so that flight is on the airline. Now, if you get confused with switching up letters, I could certainly have used up here, instead of Y, I could have used flight, and I could have used flight, and here I could have used airline, but there's nothing wrong with using X and Y just to be general up here, and then making it more specific when we get down here. So this is our statement. There exists a man such that for all airlines there exists a flight such that the man has taken the flight and that flight is on that airline. So now that we have this massive, crazy sentence or statement, I want to negate it. So I want to know, how would I negate this with all of these nested quantifiers, which we practiced in the last video? And then what does that new statement mean? So remember, with negation, we've got this negation here, and my job is to make sure that it's not in front of any of my quantifiers, and basically that I've simplified it as much as I possibly can. So I'm going to start by replacing this with for all M, and then not everything else. So not for all A, there exists an F, etc., etc., etc. All of this remains the same. doing lots of copying and pasting. And now I still have for all M, so for all men. And now I'm negating for all airlines. So how do I negate for all airlines? There exists some airline such as the rest of this is not true. So again, all of the rest of this just gets recopied, recopied, recopied. I just want to keep moving it in as far as I can get it. What's next? Well, now I can negate there does not exist a flight. And what is the negation of there does not exist a flight? Well, this stays the same, this stays the same. And I'm saying for all flights, not everything else. Now, the last time we practiced a negation together, we stopped right here because all of the stuff on the inside, we just put a not in front of it and we were done. But now, hopefully, we see that we've got a little rule here, De Morgan, that says, hey, you know what? I can actually distribute that not to the inside. So I can say, for all M, there exists an A, such that for all F, and then I can say not P, M, F, and then of course I'm going to switch this to or because that is what De Morgan's law says, and then I'm going to say not, I've got too many colors going on, Q, F, A. So that is as far as I can go. So this is the negation of the statement. And what on earth does that mean? That means for all men, there exists or there is an airline such that for all flights, the man has not taken the flight or that flight is not on that airline.
Up next, we're going to take a look at the rules of inference for propositional logic.